Check it out now, y'all.
nanoHUB-U online instruction.
Welcome. This is the fifth lecture of the final week of the material science of batteries. I'm going to summarize the week. So what did we learn this week? We were talking about the concept of electrical and ionic conductivity in the case of only charge flowing through the system. When you have a voltage drop, you will have a charge, and that's related to the conductivity of the system. And that conductivity is a result of the linear superposition of all the possible mechanisms that are occurring in the system. Say if you have electrons and lithium ions and different types of defects, as they contribute to the conductivity, you can add them into the system, allowing you to thus define the conductivity as a function of the diffusivity of the system, and then specify the transference number. This is specifically important or specifically relevant in the electrolyte, which is the substance that you use to mix the particles of active material with so that you can have faster intercalation and deintercalation. And we really want to make these total conductivity as large as possible so that giving a voltage drop, we maximize the charge that is exchanged between anode and cathode, and therefore increase the power and energy density of the cell. Okay? There are different types of electrolytes. They can be summarized in polymer base and ceramic base. The advantages of the polymer base, which is, by the way, the one that is used the most, is that easier to process, is very cheap, which is one of the reasons of why it's used so much. It has very high conductivities at lower temperatures, and it's usually the choice of industry to make batteries and to make them flexible. One of the disadvantages is that you can reach 120 degrees centigrade, and that's enough to basically reach the threshold of being flammable. And because they're mechanically compliant, unless you put cases that are stiff, it's very easy to pinch them. And because these organic electrolytes can catch fire when exposed to oxygen, when exposed to air, then you really can have a problem here unless you do something about the casing where you put your battery. Now, as an option to this, people have started to develop recently ceramic-based electrolytes. The main advantages is that they have a higher elastic modulus, making it harder to pinch. They are temperature resistant, meaning that you can not only reach 100 degrees C, you can go all the way to 500, 400 degrees, depending on the chemistry, of course. And the system, this ceramic type material will be much more stable. It's a great choice for thin film designs. It allows you to not only suppress these additional side reactions you don't want, it mechanically allows you to suppress the transport of dendrites. And its main disadvantage is that it performs poorly at low temperatures. Basically, if you go below the 0 centigrade, then you can get into trouble there because the conductivity becomes so low that really you get very little power. And because they're so mechanically stiff, it becomes difficult to process. Now, the electrolyte alone will not get you the performance you want. Typically, what you do is you put some salts and additives. There is a range of them. The one that is the most used is LiPF6 because it allows you to improve the ionic conductivity. There are other salts that people put like LiBob and LiClO4. Why? Because it allows you to increase the temperature performance, to make it more stable, allows you to stabilize the SCI as we have discussed in the past. And some of them actually, well, really what you want is to enhance the ionic conductivity. Others are used simply to improve its capacity because they're fire retardant, okay, and because you can inhibit corrosion or to get higher performances. Now, based on that, we propose the concept of reaction zone that to describe the performance of a cell. And here, what we basically did, we divided the electrode into a reacted and unreacted zone that it's moving at some velocity and it's defined by this position x of r, that is a function of time, okay, and the cell in this case is defined as being completely discharged when x of r reaches all the way h of c, when we have reached the cutoff voltage, or we have effectively short-circuited the system. The reaction zone is such that at t equals 0, basically we have a sliver, basically everything is available, and the discharge time that allows us to specify that the whole cell has been used. Okay, if we balance how much charge is coming here, which is basically effectively the current times the time as the charge is coming here, and relate that to the capacity of the particles and the porosity of the system, then we can readily specify, in this case, the reaction zone position as a function of the current density, the charge, basically think of it in terms of the range of solubilities, the solubility limit of the cell, and the porosity of the cell. If you do that, then you can go and balance the different contributions for the cell. You can talk about the losses that occur from the separator and the increasing loss as the particles of material leave to this tortuous path through which the ions have to go through, basically from here to here until they react over there. And these two contributions are the two main contributions for the losses from the equilibrium potential, as we have derived it as well. Okay, specifying with that the potential of the cell in the absence of diffusion limitations. So if we do that, we can come up with a very straightforward description that you can see here, how the voltage then becomes a function of time. The losses through the separator are effectively linear with current, and the losses on the electrode itself are quadratic with current and linear in time, and because of the way that we account for both the tortuosity contributions to losses and the losses as a result of the reaction zone, then we clearly have an optimum value of porosity at which the battery will deliver its optimal power density. There's a combination of thickness, porosity, and properties that you can specify to deliver that. So that the voltage versus capacity curve is going to be effectively a function of the architecture of the cell. So for a classic layered system, the vertical drops, the first approximation, are a result of the contributions from the battery that are effectively non-active, okay, and they will increase linearly as the current increases, and the slope of the cell in the absence of a voltage of the equilibrium potential depending on the concentration will be effectively, that slope will depend effectively for each of the electrodes of the current density that we specify. Okay, now this allows you to already define how the different parameters are specified, but it also sheds some light as to the main drawbacks of the classic design. Okay, the main problem of this system is that because we're putting this distribution of particles and we try to mix to make this composite set of layers, it's hard to control random events. Ions will always have to traverse the entirety of the cathode, separator, anode layers, and that becomes especially a problem in the limit of thick electrodes. So the thicker the electrode, the greater the theoretical energy density, but also the greater the losses, because you will get more and more losses as a result of those ions having to traverse through. And the total energy will always be diluted as a result of having to use these powders. Okay, and of course, as a result of the dilution, the whole cell becomes bulky. So what people have done, and they have gone below the classic window where batteries are used, which is somewhere between 30 to 60% porosity, and instead they have tried to go below the 20%, sometimes 10% or lower, and they bring back high transport limitations by performing tricks such as adding this additional linear porosity in the system, which allows you to basically engineer the spacing between pores, the size of the pore itself, and therefore increase the capacity of the cell. Other designs try to blur the boundary of where the anode, separator, and layer are, and instead try to bring them much intimately closer to minimize those losses. This leads to the concept of a 3D battery architecture, where basically by removing the electrolyte carbon binder mixture and instead putting this electrolyte layer in between, you can basically exchange lithium directly through very short distances. Okay, and here you can see different architectures as we have discussed them, each of them having their potential advantages and disadvantages. Okay, in this case you can see these layered structures, or you can think of, for example, these rods, where one, say, cathode rod would be in the neighborhood of a set of anode rods, so they can exchange sideways lithium with its surroundings. And in this case, the electrons we transfer along the length of the rod, which could have their own advantages as to how you can improve the performance. And another case, of course, doesn't have to be like that. It could be that you have your anode rods coated with electrolyte, and then the rest of the system is just embedded in a cathode block, allowing you to basically have this bicontinuous structure where you can maximize the performance. And you can see you can clearly get away from the classic structures and use all the technology for making MEMS and try to come up with designs that will have a higher density per structure. Other structures that people have been trying to define are what are referred to as self-organized batteries, where in this case you want to still maintain the bicontinuity of both the cathode and the electrolyte. And things that people have tried is things like, for example, foams, okay, where the foam structure itself can become one electrode. Then you coat that with another material, say with electrolyte, and then you fill in the remaining of the gaps with a counter electrode, so that you can have this bicontinuous structure where the cathode always has an ohmic connection with the correct lead, and the anode also has a connection, so that you can always intercalate between them. Okay, this will give you a mechanical sturdiness. However, there are, of course, always some technical challenges in making this. Okay, then we have the flow batteries, where basically what you do is you bring anode material to one layer where you would exchange lithium ions, and you have the cathode flow, the cathode slurry coming through another part, and in between you basically exchange ions while getting the charge out. This gives you the opportunity to basically always have maximum reactivity, because the particles closer to the counter electrode will exchange lithium fast and will always be ready to be utilized. But it requires you to guarantee that these tubes are never clogged, that flow can always pass through. And it really gives you an opportunity to get away from the classic designs where everything is stagnant and fixed. Then, of course, we went back and tried to put all the different pieces together as we have been describing them in these 5 weeks. And here you have, by using theory of reversible thermodynamics, terms such as a diffusion contribution, an electromigration contribution, and an osmotic pressure or chemical wind contribution that allows you to basically assess the contribution for every single driving force in the limit of small deviations away from equilibrium. Okay, and if you do that for each of the individual species, okay, then you can have a thermodynamically consistent description of how the material responds. Okay, this is for the chemical species. For the electrical and ionic contributions, what we have described about the conductivities remains. However, now you have, besides the voltage drop, you have these chemical contributions. You can think of having the conductivity term and the electromigration term, that in this term may help you transport further the charge or slow you down in the exchange of charge in the system. This will make the distribution, the description of charge in a composite electrode, regardless of what the architecture is. Very accurate, but geometrically very complex, because now you have to specify properties for every particle, every electrolyte point, every separator region, every cathode, and basically resolve for every single Butler-Balmer relationship at every single interfacial point, regardless of its geometry. So instead of doing that, what the community has done is realize that they can microstructurally average, in the context of designing these three-layer structures, the properties of each of them, and by making assumptions that particles are perfectly spherical entities, that the particle-particle interactions occur via the electrolyte, and that every point of the electrode can be its equivalent microstructurally, because we assume uniform porosity, uniform electrical conductivity and diffusivity. Then we can take one representative unit of what happens in one particle, solve that separately, decouple it microstructurally from the rest of the structure, and be able to describe what happens in the overall electrode. And by doing that, of course, and including the right conductivity properties and assumptions of how you have always transport pathways, you can effectively describe the transport in the cell. Now, if you do that, you will have to recast your kinetic equations. Okay, you will not only have to account for mass accumulation or mass conservation, but you have to account for the lithium that accumulates in the electrolyte, plus the lithium that is exchanged between representative particles and the electrolyte. Basically, you have to define the lithium exchange with the particles, which numerically in this case, or mathematically, we describe in terms of this divergence term, and the Butler-Balmer relationship that now occurs at every single point along the thickness of the electrode, times the reactive area per unit volume that gives you the strength of that reaction as it's taking place. Okay, you can do the exact same thing for the anode of the cell. Okay, and sorry, for the charge of the cell, and in this case, the charge accumulation corresponds to how the charge is diffusing in the electrode layer, and how much of that charge actually indeed is exchanged between the between the electrolyte and the particles. Mathematically, it has the same form, where you have a divergence of the flux and a term that accounts for how much charge has been exchanged with the surroundings, with the particles and its surroundings. And if you do that, and if you identify well every term, you can account for well, in this case, the average properties of each of the phases, average conductivity, average diffusivity, average electromigration contributions, which indeed correspond to, in the limit of perfectly spherical particles, to a Brugman-type relationship, as we have discussed it in the past. These kinetic equations allows you also to describe flux inside the particle, the representative particle for each of these electrodes, using Fick's law. And where at the interface now we have that Butler-Balmer relationship, okay, where that allows us to specify how much charge has indeed been exchanged with the surroundings, or mass in this case, and by using that the flux is proportional to the concentration gradients, we can indeed represent, in the absence of phase transformations, the description of mass in the system. Now, this allows me to, overall, allows us to be able to understand more clearly how a battery responds, and then identify the vertical drops from each contribution, and we can see how these contribute to all the parts that are ohmic, that is, they're not electrochemically active, and how the shape really corresponds to not only for as a result of the transport and accumulation of lithium through this porous structure, but what happens in each individual particle. Okay, and based on that, then we can go back and try to pick better chemistries, or design better chemistries, to increase the capacity of the cell and bring these losses to become as small as possible. Okay, usually these are designed for cells that go from 1C or smaller. Basically, we would like, of course, to use batteries that last 10 hours or last 2 hours, okay, depending, of course, on the application. Okay, it's not the safe to drive a car where we run out of juice after 1 hour than after we drive safe for 5 hours. Okay, that will basically give us a big difference in performance. And it all boils down really to what happens locally in the cell, how we pick different chemistries, okay, and how all of these pieces come together to specify an architecture. So overall, during this semester, we learned a lot of very interesting things. During these 5 weeks, we understood what the lingo was in the description of the system. The batteries and electrochemistry in general has its own special language that has developed over the last 50 years. We were able to connect the processing on how a battery is made to how it looks at the end. Why, for example, we use powders, why people want to maximize the area per unit volume of the cell, why they want to minimize the losses, and from those parameters, what controls, from the material science point of view, what controls the energy density and the power density, and how we really don't want one type of battery to fit every single application, but that depending on what we want to pick the right cell for the right system. Not only because of the material limitations, but also because as we pick a large battery that will have large losses, will give us high energy density, that will also lead to the appearance of different failure mechanisms that may limit the life of the cell, leading then to the opportunity to really give you a different outlook on what a battery is, right, and how it performs. I showed you this slide at the very beginning of the course, and at a first look, you really have the impression that this cell, the particles are randomly distributed, and it's all very serendipitous. This cross-section from Quinn Horn really shows us a lot of stuff of what's actually occurring in the cell. Not only of why these particles, for example, are aligned. We discussed how the compaction becomes an important process on increasing the energy density. You can see how the particles are effectively non-spherical, yet we think about it in those terms to be able to rationalize it better, and how we have these particle size inhomogeneities that are unavoidable as a result of processing, but lead to specific losses of the cell. If you look close in the slide, you will see that there are color differences between what happens in the anode and what happens in the cathode, in the separator. Those gray difference in gray regions really shows you, this difference in gradations in gray really shows you that the separator itself has its own internal structure, and that internal structure is specified based on what you want that separator to be, how this layer has to be very thin, and how actually in this case this layer has apparently 3 internal layers inside as a result of what people designed in order to maximize their performance. And the anode itself, you can see, at least it gives the impression that it has been cycled several times because of these flaky-like regions as a result of the failure mechanisms. And we clearly have learned how, by looking at these structures, we can find different thicknesses, different particle sizes, and basically giving us the first step, basically, puts it at the beginning on how we can analyze and rationalize these structures. Clearly, this field is a moving entity, a living entity. There's a lot of progress going on, but the fundamental concepts that allows you to describe how a battery responds are expected to be, because of its fundamental value, I don't expect them to change much. So you can use them as a starting point to analyze better batteries. It's a huge field. And with this, I really intend to say that there's a lot of things that may be going on that I didn't quite cover in these 5 weeks. But I hope that from this class you are able to use that as a starting point to read the literature and or to make decisions when you purchase a cell or you start doing research on the cell as to how to improve on it. And I had a lot of pleasure working and developing these lectures, and well, I hope that you enjoy watching them. If you have any questions, please send me an email. I'm always around, and well, anyway, hope talking to you at some point. Thank you.